So this is the fundamental equation. From that we found circulation small gamma where A naught AN is given. Once you know the small gamma, then we found capital gamma for the unsymmetrical aerofoil. From that we found lift and CL in different form. Then moment from that CM. From that we found XCP. Then coefficient of moment at the Portugal point. These things we found yesterday. So in the exam, if you are coming for offline mode, sometimes they will ask, write the derivation for symmetrical aerofoil or write derivation for unsymmetrical aerofoil. So this is symmetrical aerofoil, this is unsymmetrical aerofoil. Sometimes they will ask, write the derivation for the flapped aerofoil, symmetrical aerofoil with the flap. So for all those derivations, so this generalized derivation can be used. So now I will explain how to convert these equations for the symmetrical aerofoil. Okay, same derivation. What is the only difference means? For cambered aerofoil, there is a slope. Okay, but for symmetrical aerofoil, the slope is 0. That is the only difference. Okay, so if these equations, if you take wherever the dz by dx comes, that term if you take it as 0, then these equations can be converted for the symmetrical aerofoil. Even though it is for unsymmetrical, if you put 0 for dz by dx terms in this derivation, you will get symmetrical aerofoil derivation. Okay, so you no need to memorize two derivations. If you can memorize these derivations, you can derive for symmetrical, flapped aerofoil, etc. See, I have taken dz by dx is 0 for the fundamental equation. So this is for unsymmetrical. From that I am getting for symmetrical. So if you cancel this, then this is the fundamental equation of symmetrical aerofoil. Then for small gamma, if you take, so dz by dx is 0. So an is completely 0, and a naught, this term is 0, remaining only alpha. So substitute here. So instead of a naught alpha, this term is 0. Then you will get 2v infinity alpha 1 plus cos theta by sin theta. This is for symmetrical. From this itself you can derive. Similarly, this is for capital gamma for unsymmetrical aerofoil. So an is 0, that means a1, a2 up to a infinity it is 0. Okay, so a1 is 0. Remaining what we have is, so instead of a naught it is alpha we found. So v infinity alpha c pi. This is for the symmetrical. Similarly for CL, dz by dx is 0. So remaining is only 2 pi alpha. So if you can remember this derivation, you can easily write it for both unsymmetrical and symmetrical. Then this is CL in another form. So instead of a naught we have alpha, this term is 0. So we have 2 pi alpha. And CM if you take a1, a2 everything is 0. Remaining is pi by 2 a naught. Instead of a naught it is alpha. We got for the symmetrical aerofoil. The same way in terms of CL. Then XCP, A1, A2 is 0. So remaining we got quarter guard point, 23%. Then CM, C by 4, it is totally 0. We also got 0. For symmetrical aerofoil, so center of pressure, aerodynamic center, everything lies at the quarter guard point. Okay. And if the aerodynamic center lies at this quarter guard point, that means moment is constant for all the angle of attack. So here center of pressure also lies on the same point. So that means moment is 0. Okay. If the quarter guard point is the center of pressure, then moment about this point is 0, and it is constant for all the angle of attack. So this point can be considered as aerodynamic center also. Is that clear? The last one. So quarter guard point is the center of pressure and aerodynamic center for symmetrical aerofoil. So like that, from one derivation, we can derive for unsymmetrical and symmetrical. Okay. So for symmetrical aerofoil, so we found XCP is C by 4, right? If 25% of the point is the center of pressure, so we know the definition of center of pressure. The total force is acting and moment about the point is 0. And we found this is constant. Whatever the angle you change, 10 degree, 20 degree, whatever the angle you change, the center of pressure location is not changing and moment is 0 for all the angle. So center of pressure is constant for different angle, 0 degree, 10 degree, 20 degree. Okay, the position is constant. And if the point is the center of pressure, then moment will be 0. Right? Now you see for different angle, the moment is 0. That means moment is constant at this point. So according to the aerodynamic center definition, the moment is independent of angle of attack. Moment is constant for different angle of attack. Here also, if you see the quarter guard point, moment is 0 and it is constant for all the angle of attack. So this point is considered as aerodynamic center also. Okay, center of pressure, aerodynamic center, both quarter guard point for symmetrical. Is that clear? So moment is 0 at every angle. So this is the symmetrical airfoil. Chord length 0 to C, or in terms of theta, if you write, it will be 0 to pi. Okay, and I'm taking a small flap at the trailing edge. I'm taking certain portion of the airfoil as a flap, okay, from the trailing edge point. Mostly it will be 20% or 30% like that. And I'm deflecting that flap to the smaller angle beta, because according to the thin airfoil theory, alpha is very small, camber thickness, everything is very small. So this beta also very small. Okay, I'm deflecting this flap to the very smaller angle beta. So from here, I'm getting this type of profile now. Previously, it is just a straight line. Now I deflected this flap. So this is the new profile I'm getting with the deflection angle beta. So I'm taking this distance is B, this is A. Simply I'm giving some names. B and A, this vertical and horizontal distance, and C means in terms of chord I have written, okay, BC, AC. In terms of chord I have written, so it is BC, this distance, and vertical distance is AC. Okay, so I have 3 points, leading edge point, okay, trailing edge point, and this is the joining between airfoil and the flap. This I am taking as B, A, B, C points. Okay, so this is flat airfoil and this is after deflection. Now you know the definition of chord line. So chord line is the distance between leading edge to trailing edge. So for the first airfoil, this is the chord line. But for the second airfoil, if you apply the same definition, distance between, that is line joining the leading edge and trailing edge. Now this is our chord line. Okay, this is the straight line joins leading edge and trailing edge. Previously it is straight line, now it is different. Okay, so this is our chord line. So 0 to C it varies, or in theta 0 to pi it varies. In between also we have some angle. Okay, now how we are taking? We are taking this is 0, this is pi. In between it will be pi by 2. Like that we will take it, right? Here also some angle will be there. We don't know that, so I have taken that as phi. Okay. So everywhere, instead of x distance, we are taking theta from 0 to pi. So at this point also, we will have some theta. So I don't know the theta, simply I have taken that as phi. So this is the diagram. Is that clear? In symmetrical airfoil with the flap deflected beta. Now this is our new chord line. Okay, 0 to pi. And this may be the pi by 2 point. And here I have some angle that I have taken as phi. Okay. And these are all the general equations that is derived from the unsymmetrical airfoil. Small gamma, where A0 AN is given. Once you know this small gamma, we can find capital gamma and CL and CM. The same equations, we are going to use this for flapped airfoil also. And you can see, if you want to find small gamma, CL, CM and all, you should know A0 and A1. Okay. And if you want to find A0 and AN, you should know the slope and alpha. Mostly alpha will be given in the problem. So you have to find dz by dx. So once you know the dz by dx, first you can find A0 and AN, then you can find all other property. This is the procedure. Okay, whatever the airfoil is given, first you have to find the slope, then find A0, A1, A2, then you can find CL, CM, etc. and all. This is the procedure. So this is our model, flap airfoil. So first step, we have to find the slope for this airfoil from 0 to B point. This is the flat plate. Okay, then the slope will be 0. dz by dx is 0. And from here to here, we have some slope. So this is dx and this is minus dz. Okay, so dx is bc minus dz is ac. Okay, cc get cancelled. So for this flap, the slope is minus a by b. Is that clear? For straight line, slope is 0. For this flap, slope is minus a by b. Okay, dz by dx. Okay, dz, sorry, dx by, dz by dx. Okay, so now we got this slope for this airfoil. Now we can go to that. So general equation. Is that clear? Should I repeat out? The slope. Online students, is it clear? How to find the slope?
Yes, sir.
Okay. So here it is 0. For this red color line flap, it is minus a by b. Okay. So with this dz by dx, first I'm going to find a0, a1, a2 and all. Then we can find all these parameters. Okay. So first I will find a0. Same equation I am taking. So this is the a0 equation. Okay. And we know we have two elements. One is airfoil, another one is flap in that, and we have two different dz by dx. So I am splitting this term into two terms, alpha minus, and this term alone I am taking 2. So from airfoil 0 to 5, one term, 0 to 5 dz by dx. Then from the flap, it is 5 to pi. Like that, I am splitting this single term as two terms because we have two elements in this airfoil. Okay, flat plate and the flap. Is that clear? Okay. So here separate dz by dx. Here separate dz by dx. Sometime if you are going for multi-element flap, maybe another one small flap, then you have to split this term into 3. Maybe 0, 5. Some angle, which angle? Okay, some alpha, some pi, like that. If it is there, then you have to write 3 terms. Okay, integral to 0 to 5, then 5 to alpha, and alpha to pi, like that. This term you have to divide into 3 terms. Depends upon the flap. So here you have only 2 elements. So I am splitting that into 2 elements, 0, 5 and pi. Okay, 0 to 5 and 5 to pi. And we know for this flat plate, it is 0. Instead of this, we have to substitute 0. And here we found it is minus a by b for this flap. So this term is 0. Now this is the remaining terms. Okay, now you can integrate it. So a by b is constant. So d theta, if you integrate it, is theta. Substitute the limits 5 to pi. You will get this term. Okay, normal integration. So one time is 0, a by b is constant. Now integrate, you will get this term. Actually, I need all the equation in terms of theta. I don't want this a b, so that also I am changing it. So if you take that flap right angle triangle, okay, so this is beta, this is b, this is a. I can find tan beta. Okay, I want to convert this a b in terms of theta. Using this flap right angle triangle, I am writing tan beta equation, which is a by b. Okay, so already I assumed alpha is very small and this beta also very small. I can write tan beta is equal to beta, which is equal to a by b. So instead of this a by b, I am going to substitute beta. Okay, then they are simply rearranged. Pi they taken inside, so they are getting alpha plus beta 1 minus 5 by pi. This is a0. Is that clear? So this term alone, they are writing as 2 terms, depends upon the elements. The normal simplification. Finally, every term they are converting as a theta in terms of degrees. So instead of A by B, we have taken beta. So A0 we found. Same procedure you will use it for the A1 and A2 also. So first we are taking AN. Once we found the AN, from that we can easily find A1, A2, etc. So this is the AN equation. Again, this term we have to split into two terms. Okay, for flat plate, this component is 0. For the flap, it is minus A by B, and theta changes from 0 to pi and phi to pi. Okay, so this is 0. So remaining term here it is mentioned. And cos n theta, if you integrate, you will get sin n theta by n. Then apply the limits, you will get this term. Okay, so pi if you apply it is 0. Then phi if you apply, you will get this term. Already found A by B is beta. Again they rearranged. So 2 sin n phi divided by n pi into beta. Is that clear? Okay, they divided into two terms. So this is 0. Only this term they are taking and integrate and simplify, apply the limits, you will get AN. So once you know the AN, we can find A1 and A2. That is, if you substitute n is equal to 1 in this equation, you will get A1. So 2 sin phi divided by pi beta. And if you substitute n is equal to 2 in the same equation, so you will get this term. So 2 get cancelled, and this is the simplified version. Okay. So we got A1 and A2. A0 also we found in the previous slide. Okay. Then substitute all that A0, A1, A2 in this generalized equations. You can find the small gamma CL, CM. And if you substitute and simplify, you will get these equations. In the first problem, they mentioned angle of attack, free stream velocity in terms of feet per second, British unit, also SI unit, meter per second. So chord length in terms of feet and meter, then CL, CM. From that, we have to find lift of the airfoil, moment at the quarter guard point of the airfoil. So it's very general formula, half rho V squared S CL, as it is the airfoil. So S is equal to simply C into 1. Okay, if it is a wing, we will get C into B. If it is the airfoil, it is simply C into 1 area. So instead of S, it is simply C. Straight away, you have to substitute everything, find the value, maybe assume 1 mark or 2 marks. But sometime you have to check the units, whether they mention in the feet or meter. Okay, if they mention 2 feet, you should not straight away substitute S is equal to 2. You have to convert this into meter, then only you have to substitute. Okay, don't forget. Check the units. Then moment about the quarter guard point, same half rho V squared S C, CMC by 4. The CMC by 4 is given. Substitute everything, you will get the values. It is just a very straight problems, lift and moment. This equation you are studying from fluid dynamics. This is also simple. Second problem. They are given chord length, velocity, lift. From that you have to find the CL. Simply L dash divided by half rho V square S. So if the density is not mentioned, you can assume, or in the answer you can write. So assume the sea level conditions, then density is 1.225 kilogram per meter cube, then you can proceed. Okay, because you need the density, it is not given, so you should not think so the data is missing. Okay, you have to write. So assume the sea level condition, density is 1.225, you have to substitute the value here, 1.225. Some people may take 1 also, it is okay, but you have to mention it, which value you are taking. So straight away you can find the CL, okay, because we know the density, velocity, S, L dash, etc. and all. Sometime what they will do, addition to this problem, they will give CL versus alpha graph. CL versus alpha graph they will give, and they may ask what is the corresponding angle of attack. Once you know the CL value, for example, the CL value is here, you have to find corresponding alpha from the graph. Either also they may ask. So this is the very general equation, general problem. You can easily answer. Sometime they will give the word thin. Okay, sometimes they will mention maybe NACA 0012 aerofoil. Okay, maybe 006 thin aerofoil, like that if they mention, then no need to go for these general CL equations. Okay, normally if they ask CL, what you will think? L dash divided by rho V infinity square S. But if they find the word thin, then you can straight away you can take this 2 pi alpha, because already we derived for the thin symmetrical aerofoil. Okay, if they mention thin symmetrical or unsymmetrical, depends upon that you can take the CL. So they may give NACA 0006 thin aerofoil. Find the CL for the angle of attack 15. So if you first this formula only will come to your mind. So you should not think only alpha is given, nothing is given, so the problem is wrong. Okay, if they mention thin, take the CL value from the thin aerofoil derivation 2 pi alpha. So 2 pi and alpha you have to substitute carefully. You know there is no unit for the CL, right? Coefficient of forces. So here alpha is given in terms of degree, 1.5 degree. You have to convert the degree into radian and you have to substitute here 2 pi alpha. So mostly what they will do, they may remember the formula and all 2 pi alpha, but straight away they will substitute 1.5 and find the value. It will be wrong, because if you substitute alpha in terms of degree, then final CL also will be in terms of degree. Okay, it is wrong. You have to convert alpha to radian, then only you have to substitute. Okay, then if they ask moment, that formula also derived minus CL by 4 for symmetrical aerofoil. So once you know CL substitute, you will get the moment. Is that clear? So wherever they mention the thin, you can use the thin aerofoil relations. No need to go for the general equations. That's it. Any doubt? Don't forget alpha, always you have to take it in terms of radian in this thin aerofoil theory problems. This is another one problem. With that, so we will finish the second unit. We'll go for the third unit next. So here they have given the camber line of the thin aerofoil, and they mentioned the camber equation also. Okay, normally it will be in terms of Z equation, because this is Z, this is X. It will be, the equation will be like Z is equal to some term will be there. But here they are given us in terms of chord, Z by C, X by C they are given. Okay, so it can be like Z is equal to in terms of X, or sometimes it will be Z by C, X by C. Both can be given in the exam. So once we know the camber equation, so we know the generalized equations, gamma, CL, CM, etc. And what you have to first find? dz by dx. Okay, always in this thin airfoil theory, first you have to find dz by dx. From there you can find an, a1, a2, etc. and all. From there you can find CL, CM. So from this z by c, I have to find dz by dx. That is the first step. Is that clear? So if Z is given, straight away you can differentiate dz by dx. But here Z by C is given, but we need to find dz by dx. So we can write this as d of Z by C divided by d of x by C. Okay, so from this equation, if you want to find dz by dx, then you have to differentiate this equation with respect to x by c. Is that clear? The normal max only. So first step, from this z by c, I am going to find dz by dx. This is z by c. We can find dz by dx. Okay, differentiate with respect to x by c. So this term is 1. This is 2x by c. So this is the equation I am getting, dz by dx. Then second step, we have to do the coordinate transformation from x to theta. You know x is equal to c by 2 1 minus cos theta. And what here we need is the x by c. So take this c to the left hand side. So x by c is equal to 1 minus cos theta by 2. So substitute here, simplify, you will get this term. Okay. So I know Z by C. From that I found dz by dx. Then convert this x by c in terms of theta using this basic equations. Okay. So finally I got dz by dx in terms of theta. Once you know that, we can find a0, a1, etc. This is a0 equation, alpha minus 1 by pi dz by dx d theta. Substitute here. You know, if you integrate cos theta, you will get sin theta. And if you apply the limits to the sin theta, this term will be 0. Right? Because limit is 0 to pi. So if you integrate the sin theta, you will get 0 term. So we can find a0 as alpha. So this term is 0, remaining is alpha. Hello? மேல போங்களா? நான் வெளில வந்துட்டேன். ஹலோ? அதான் நான் வெளில இருக்கிறேன். நீங்க மேல போக முடியுமா? ஓகே, தேங்க்யூ. So next one is an. So again same dz by ds we have to substitute here now. Okay, instead of that 4h cos theta. So here it is integral cos square. So the value is pi by 2. Okay, here they mention the steps. So straight away you can substitute. So instead of this it is pi by 2. So it will be 2 divided by pi 4h pi by 2. 2 pi by get cancelled, remaining is 4h. Okay. Then a2, instead of dz by dx, it is 4h cos theta. And here they mention the value of integral. Integral cos theta cos 2 theta. This is how we will integrate. Then apply the limit, you will get 0 because of sin term. So a2 is 0. Okay. So these things are all normal mathematical steps only. So from z by c, we found dz by dx. Then in terms of theta, then substitute in this a0, an, a1, a2. You can find the values a0, a1, a2. Then you can straight away substitute here. So a0 is alpha. All that a1, a2, everything is 0. No, sorry. I think a0 is alpha, we got it. And a1 is 4h and a2 is 0. So substitute in the general equations. This is alpha, a1 is 4h. You will get these equations. Similarly, here you substitute, this is alpha, this is 4h. Simplify, you will get this equation. So this is also 12 marks. Okay. So instead of this parabolic, they will give different Chamberlain equations. Same procedure. It's like a mathematical problem only. From this equation, you have to find dz by dx, then a0, a1, a2, small gamma, cl. Is that clear? This problem? 12 marks. No doubt. Then. So this is with the numerical values for the same problem. So same parabolic Chamberlain equation, and this is the h. So here you see this h mentions the maximum thickness. Okay, this h means maximum thickness. So in the problem they mentioned the h value 0.05 meter. Velocity density is given. Lift also given. And they are asking us to find the angle of attack. As it is a thin airfoil, and we found this equation just now. So 2 pi alpha plus 2h. So we know 2 value, pi value, h value, only alpha you have to find it. And for that you should know the CL value. Okay. All other are known value. Once you know the CL, you can find the alpha from this equation. And we know the lift, from that we can find the CL. Lift is half rho v square s CL. So rearrange. So lift divided by half rho v square s, okay, half density is 1.23, velocity is 50, and chord length is 1 meter. Substitute everything, you can get the CL. Substitute the CL here. CL is equal to 2 pi alpha plus 2 into h. Rearrange, you will get alpha in terms of radian. Always from the airfoil theory, the alpha, whatever you are getting, is the radian that you have to convert into degree.